It may have occurred to you that area moments can have a continuum of values, since we can position the origin of a coordinate system anywhere we want and in any orientation. What would be valuable is a single set of area moments that form a basis for generating other area moments about any set of axes. Such a basis is available in area moments defined at centroidal axes. Here the primed coordinate system is the centroidal coordinate system with origin at C. The unprimed xy coordinate system is at some arbitrary location, but the two coordinate systems are parallel to one another. The importance of the axes being parallel can be seen in the relatively simple relationship between two different methods of describing the same material point. A material point, a distance y, from the x-axis is also described as y prime plus dx. Under these conditions, the area moments about an arbitrarily positioned xy coordinate system can be expressed in terms of the centroidal area moments according to these expressions. It is critically important that the first term on the right-hand side of these expressions be the centroidal area moments. This expression cannot be used as is to relate the area moments about one non-centroidal coordinate system to those about a second non-centroidal coordinate system. The proof of these results is straightforward and brief. Substituting y tilde equals y tilde prime plus dx into the integrand of ix, expanding the square and separating terms, we find the first term is centroidal ix prime, the last term is dx squared a, and the middle term goes to 0. The middle term does so because yc prime a is equal to this integral, where yc prime is the y position of the centroid in the prime centroidal axes. But this location is, by definition, 0. So we are left with ix equals ix prime plus dx squared a. We can now also see why the smallest values of area moments are those about the centroidal axes. The terms dx squared a, dy squared a, and d squared a are all inherently positive. The smallest values they could have are 0, which only occurs if the xy and x prime y prime axes are coincident. Therefore, the minimum values of area moments are those about the centroidal axes. What is the parallel axis theorem good for? It is mostly valuable for generating area moments of cross-sections that can be represented as a superposition of relatively simple shapes. Let's go back to our I-beam. We often need the area moments about the shape's centroidal axes, shown as the blue X in this figure. We really don't want to be condemned to using the integral definition to perform this calculation, and fortunately the parallel axis theorem provides a remedy. We can think of the I-beam cross-section as the superposition of three rectangular areas. The web is a vertical segment whose centroid coincides with the centroid of the whole composite shape. Each flange is a horizontal segment whose centroid is displaced from the shape centroid by a distance equal to half the web height and half the flange height. We could write out expressions in symbolic form for the area moments about the I-beam centroidal axes. As a reminder, we have these centroidal expressions for area moments of rectangular shapes. We'll let this distance be the span of the webbing, and this distance be the height of the webbing. It's often the case that our I-beam is symmetric about top and bottom. The flanges have the same dimensions. So we'll let this distance be the span of the flange, and this distance be the height of the flange. Again, let's keep in mind that the centroids of the individual shapes that make up the I-beam are here as red dots. We have a local coordinate system that goes with each one of those. And what we should note from that is that the x-axes are offset by certain distances. So the flanges have x-axes that are parallel to the x-axis of the shape, but are displaced by a certain distance that we'll write down in a second. All of the y-axes, however, are aligned. There's no separation between the different y-axes. They're all essentially coincident. But we do have this difference in the local x-axes that will factor into our expressions for the area moments. For Ix, we have contributions from the web and in each flange, and because the centroid of the web is coincident with the centroid of the whole shape, there will be no parallel axis contribution. This will simply be the span of the web times its height cubed over 12. Because the flanges are equal, we'll just put a 2 out here and write an expression for each one. We'll just put a 2 out here and write an expression for one flange then. Its centroidal area moment is BH cubed over 12. And then the parallel axis offset is the area times the distance between parallel axes squared, and that distance is half the web height plus half the flange height. For Iy, all of the local y-axes are aligned, and we simply have the centroidal values for each shape. So we have the height of the web times its span cubed over 12 plus 2 times the height of the flange times its span cubed over 12. Expressions like this permit us to write area moments for complicated shapes using tabulated values of centroidal area moments in conjunction with the parallel axis theorem. And I just noticed that I made an error here as I was writing this down, so let's emphasize that this is BH cubed over 12. In addition, there is nothing about the parallel axis theorem which requires the span in our rectangular expressions to have a certain size. The span B could be finite, it could also be infinitesimal. We could use this to work around our previous limitation on 1D integrals. For our vertically oriented rectangular strips, we could write, for instance, an increment of area moment about the x-axis equals the increment of area moment about the centroidal axis of the rectangular strip plus a parallel axis offset, which consists of the incremental area of the strip times the distance dx between the center of that strip and the x-axis, which in this case is the centroid of the rectangular strip y tilde. Assuming the top and bottom bounding curves are described as known functions, y top and y bottom of x, we get the boxed expressions at the bottom of this slide. Now let's return to a previous example to confirm we get the same result whether we use a 1D integration in x or in y. Note that y top and y bottom are given by these expressions, and to use our boxed expressions previously, we'll need this difference, which is x minus x squared over 5. And we also have the centroid of the strip, which is 1 plus x over 2 plus x squared over 10. Then, using our expression, the area moment about the x-axis is the integral from 0 to 5, 1/12 of y top minus y bottom cubed dx plus the integral from 0 to 5 dx squared times the area increment h dx. There may be a bit more work multiplying out these polynomial expressions, but no exotic integration procedures are required to evaluate the integrals. If we multiply these things out, what we find are the following results. X minus x squared over 5 cubed can be expanded as this expression, which you may want to confirm for yourself. The expression in the second integral can be written as this polynomial. Evaluating those integrals, we get the following two terms. Evaluating the results, we get these two contributions. And I've kept them separate because this first term represents the centroidal contributions, the sum of the centroidal contributions from all of our vertically oriented strips, and that is, I'll call that C for the centroidal contribution, and that turns out to be 0.372 in units of inches to the fourth. And then this term is the parallel axis contribution, or the sum of the parallel axis contributions from all of those differential elements, and that turns out to be 42.78 inches to the fourth. So clearly the parallel axis contribution is dominant, and that sum gives us the same result that we had before, which is that Ix is 43.15 inches to the fourth.